Imagine waking up at 3 in the morning.
Oh, the classic nightmare.
Right. Your phone is just buzzing off the nightstand, the pager app is screaming at you, and your heart is like instantly in your throat.
Yep, we've all been there.
You jump on the incident response bridge, and there is absolute chaos. I mean, the company's manufacturing floor has ground to a complete halt.
Which means money is just actively burning.
Exactly. Because the real-time operational dashboard went totally dark. Millions of dollars of inventory just sitting there. And, well, you're the cloud architect on call.
No pressure, right?
None at all. So you're tearing through the logs. You're looking for, I don't know, a complex cyber attack or maybe a massive regional AWS outage.
But it's almost never that.
It's not. You know what the root cause actually ends up being? Someone on the engineering team thought that, because they were using a quote-unquote serverless data integration service.
I know exactly where this is going.
Right. They thought they didn't have to configure a basic VPC route table. A missing text string in a routing configuration brought down an entire factory.
It happens so much more often than anyone in the industry actually wants to admit.
Yeah.
We get so abstracted away from the bare metal these days that we kind of forget the fundamental laws of networking and compute. They still apply.
They really do.
Yeah.
So welcome to the deep dive. Today, we are putting on our hard hats. We're treating you, the listener, not just as an audience member, but as a fellow cloud architect sitting right next to us in the trenches.
Grab a shovel.
Exactly. We're wading into the deep end of the AWS Certified Data Engineer Associate exam, the DEA-C01. But look, we are not here to read you a syllabus.
Yeah, definitely not. If you want rote memorization, I mean, the internet is absolutely full of flashcards.
Yeah, you don't need us for that.
Our mission today is to really deconstruct the systems engineering why behind the most complex scenarios you'll face, both on this exam and, frankly, in real production environments.
Right. We want to actively dismantle those hive mind assumptions you see floating around on developer forums.
Oh, the forums are dangerous.
They are.
Yeah.
It's all these legacy anti-patterns and cognitive pitfalls that lead incredibly smart engineers completely astray. Because passing an exam on a Tuesday is one thing, right?
Yeah.
Building an architecture that actually lets you sleep through the night on a Friday is another thing entirely.
That's the real goal. And when you look at the community debates around these complex data scenarios, you see engineers just completely split.
Yeah, arguing over dead ends.
Exactly. They are confidently walking into architectural dead ends. My core philosophy when evaluating any cloud architecture is that you have to look beyond what just seems functionally correct in a vacuum.
You have to know what's happening under the hood.
You really do. You have to understand the mechanical reality of how a managed service operates. The incorrect approaches you see proposed online aren't usually just random guesses.
Right, they're usually based on something that used to work.
Exactly. They're cleverly disguised legacy patterns that, might have been best practices a decade ago, or they represent a fundamental misunderstanding of the abstraction layer.
Yeah, and if there is one golden rule, one ultimate tiebreaker in modern cloud engineering, it's the concept of least operational overhead.
Always.
When forced to choose, the cloud fundamentally rewards you for writing less custom code, managing fewer instances, and really leaning into native integrations.
It's about letting AWS do the heavy lifting.
Right. Okay, let's unpack this. Let's start at the absolute foundation. Before you can transform a petabyte of data, before you can run ML models, you have to actually connect to the data.
Networking 101.
And this is where the serverless illusion claims its first victims. Engineers see the word serverless, and their brains immediately translate that to, well, no network configuration required.
It is a profoundly dangerous illusion.
Yeah.
Serverless simply means AWS is managing the underlying OS patching, the hypervisor, the physical hardware.
Right, you're not racking servers.
Exactly. It means you don't have to SSH into a Linux box. But it absolutely does not mean the laws of TCP/IP and networking physics have just ceased to exist.
So true. Let's ground this in a real-world scenario that you will definitely see variations of. Say a data engineering team sets up an AWS glue job.
Okay, classic ETL.
The goal is simple. Extract data from a secure Amazon S3 bucket, run some PySpark transformations, and load it somewhere else.
Makes sense.
So they do the IAM dance perfectly. They create a role, attach policies granting read access to the specific bucket, and attach that role to the glue job. They hit run, and boom.
Let me guess. It fails immediately.
It fails immediately with an error complaining about an Amazon S3 VPC gateway endpoint.
Oh, man. If you read the forums when this specific error pops up, it's a fascinating study in misdiagnosis.
It's wild. What do they usually say?
Well, a massive contingent of developers will immediately insist that the problem is a bucket policy.
Because it's S3, so it must be permissions.
Right. They argue that because glue is serverless, it exists kind of outside of traditional networking constructs.
Like it's floating in the clouds.
Exactly. They think it doesn't use security groups or subnets, so the rejection must be an identity and access management issue. They want to go write this complex JSON bucket policy, explicitly allowing the glue service principle.
Which is completely wild when you understand how the service actually provisions resources.
It really is.
Let's clear the air on serverless networking within a virtual private cloud, or VPC. When you configure a glue job to run within your private network so it can reach your internal databases.
Which is very common.
Yeah, very common. Glue is not just floating in the ether.
Precisely. Under the hood, AWS is actively spinning up instances. They're usually utilizing Firecracker micro VMs.
Right.
So when you tell Glue to run in your VPC, AWS essentially reaches into your designated private subnet and drops in an elastic network interface, an ENI.
An actual a virtual network card.
Exactly. That ENI consumes a private IP address directly from your subnet's CIDR block. And because it is an ENI sitting in your subnet, it absolutely must be assigned a security group.
To dictate what port traffic is allowed in and out.
Yes. The premise that serverless means no security groups is just a fundamental misunderstanding of the AWS hypervisor model.
But let's look closer at the actual error in this scenario. It's specifically called out a VPC gateway endpoint.
Right.
So if the IAM role is perfectly fine, why are we digging into network configurations? I like to think of it this way. IAM is like having a top-tier, all-access VIP ID badge to get into a highly secure building.
Yeah, I like this.
You are fully authorized to be there, but the VPC route table, that's the physical road connecting your house to that building.
Yeah.
You can have the best ID badge in the world, but if there is no road, no bridge, no physical path to travel, you aren't getting to the front door to even swipe your badge. You need both identity authorization and network reachability.
That is the exact distinction engineers need to internalize.
Yeah.
Confusing identity-based access with network reachability is one of the most common architectural dead ends.
So how does the gateway endpoint fit into the road analogy?
Well, an S3 VPC gateway endpoint is a specific routing construct. By default, S3 is a public regional service.
Right, it lives on the public internet.
Exactly. So if your glue job is in a private subnet with no internet access, it literally cannot route traffic to S3's public IP addresses.
Because there's no road.
Exactly. A gateway endpoint fixes this by adding a private, direct route to S3 entirely within the AWS global network backbone.
And it does that without needing a NAT gateway or an internet gateway.
Which is huge, because NAT gateways are expensive.
Oh, man. If you were pushing terabytes of data through a NAT gateway just to reach S3, your CFO is going to have a very unpleasant conversation with you at the end of the month.
For sure. Gateway endpoints for S3 are free, but they require a specific configuration step that people constantly miss.
The route table update.
Yes. The solution to this scenario isn't touching IAM at all. You have to go into the VPC's route table, the actual map of the network, and verify that there is a specific rule targeting the Amazon S3 prefix list.
Basically telling the network where to send the traffic.
Exactly. The route table has to explicitly state, if traffic is destined for an S3 IP address, route it through this gateway endpoint. If that single line is missing, the packets just hit the edge of the subnet and drop into the void.
The ID badge is useless without the road. That is such a critical mechanism to understand.
It really is.
So, okay, we've got the network routed correctly, the road is paved, the data is flowing from S3. Now the architectural conversation shifts. How fast does that data actually need to flow?
This is where things get really interesting.
Yeah, because this brings us to a massive cognitive pitfall, misunderstanding the latency spectrum, specifically the hard engineering boundaries between real-time streaming and near real-time micro-batching.
Oh, this is a conversation where we separate the data mechanics from the true systems engineers.
Absolutely.
Because in marketing materials, real-time is thrown around so casually. But in systems architecture, that terminology dictates your entire technology stack.
Let's dive into a high-stakes operational scenario. We have a manufacturing company collecting telemetry data like temperature, vibration, pressure from thousands of sensors on a factory floor.
Okay, lots of noisy data.
Tons of it.
Yeah.
They ingest this data using Amazon Kinesis data streams. From there, they use Kinesis Data Firehose to dump the raw data into an S3 bucket for long-term storage.
Standard pattern. That part works flawlessly.
Right. But here is the critical business constraint. The plant manager needs a real-time view of operational efficiency displayed on a massive screen overlooking the factory floor.
They want the dashboard.
They need the absolute lowest latency possible. Sub-second updates, I mean, if a machine starts vibrating out of tolerance, they need to see it instantly before it literally tears itself apart.
And when you look at how developers approach this constraint, they almost always try to shoehorn the tools they are most comfortable with rather than the tools built for the constraint.
Yeah, what's the usual wrong answer here?
You will see an entire camp advocate for a typical event-driven architecture. They'll say, okay, let's configure an S3 event notification.
Okay, wait, I already see the problem.
Right. They say, every time Firehose writes a file to S3, we trigger a Lambda function. That Lambda parses the file, writes the metrics into an Amazon Aurora relational database, and then we hook up Amazon QuickSight to Aurora to build a dashboard.
Oh my gosh, wait, I can hear the latency adding up just from you saying that sentence.
It's an operational nightmare for sub-second latency.
Yeah, there are so many hops.
And then the other camp tries to simplify it, which is better, but still wrong. They say, let's skip S3, let's just point Kinesis Data Firehose directly at Amazon TimeStream, which is a time series database, and dashboard it from there.
Which sounds faster on paper.
It does, but both of these approaches are fatal architectural flaws for this specific use case.
Let's break down exactly why. Because, I mean, Lambda is fast, Aurora is fast. Why does this fail the plant manager's constraint?
It fails because it ignores the fundamental mechanical constraints of the services themselves. Let's start with Firehose.
Okay.
Kinesis Data Firehose has data and Kinesis in the name, so people naturally assume it's instantaneous.
Like a stream.
Exactly. But it is not. Firehose is definitively, architecturally, a near real-time service.
Near real-time.
Yes. Its entire purpose in life is to buffer data. It collects records over a specific time window, say 60 seconds, or until it hits a specific size limit, like 1 megabyte.
Right, it waits.
Then and only then does it compress those records and write a batch to a destination. The exact millisecond you introduce Firehose into a pipeline, you have forfeited real time.
You are inherently accepting at least 60 seconds of delay.
You are actively, intentionally choosing microbatching.
Ah, so before the data even lands in S3 or a database, you've already lost the race. The machine is already vibrating itself into pieces, while Firehose is politely waiting to fill up its 1 megabyte buffer.
Precisely. The damage is done. And let's look at the visualization layer people suggest, which is Amazon QuickSight.
Great tool, generally speaking.
Phenomenal business intelligence tool. It uses the spicy engine for massive, super-fast in-memory calculations on historical data. But it is fundamentally designed for BI reporting.
Like generating weekly sales reports or interactive analytical dashboards?
Exactly. It is not purpose-built to act as a sub-second flickering lights operational monitor on a noisy factory floor. It relies on scheduled refreshes or direct query polling.
And polling introduces unacceptable latency for an anomaly detection dashboard.
It's just the wrong tool for the job.
So if buffering is the enemy and polling is the enemy, how do we actually satisfy the constraint? What is the pure real-time path?
The only architectural pattern that survives this constraint is to keep the data entirely in motion.
Okay, how do we do that?
You take the initial Kinesis data stream, which is genuinely real-time, offering millisecond latency, and you completely bypass Firehose for the dashboard path.
Oh, just skip it entirely.
Yep. Instead, you attach Amazon Managed Service for Apache Flink directly to the stream.
Ah, Flink. Used to be called Kinesis Data Analytics, right?
That's the one. Flink allows you to write SQL or Java code that continuously processes the stream in memory.
So you never write it to disk.
Exactly. It maintains state, calculates tumbling windows, and identifies the anomalies while the data is still literally flying through the network.
That's incredible.
And from there, Flink pushes that aggregated metric instantly into Amazon TimeStream. Now, TimeStream uses a magnetic tier for old data, but crucially, it has an in-memory store for recent data.
Perfect for sub-second retrieval.
Exactly. And finally, for visualization, you don't use a BI tool like QuickSight, you use Grafana.
AWS Managed Grafana natively integrates with TimeStream, right?
It does, and it's specifically engineered to auto-refresh and display real-time time series telemetry. It holds a persistent connection open. Stream to Flink, to TimeStream, to Grafana. No buffering, no batching, no polling.
That is just a masterclass in pipeline efficiency. And it brings up a broader concept I really want to explore here. Let's look at another scenario that highlights this exact philosophical shift.
Let's hear it.
So we have a telecommunications company. They are collecting network usage data across millions of cell towers, thousands of data points a second.
Massive scale.
Massive. Currently, all this data hits an Amazon Aurora database. The business logic dictates that sudden, massive drops in data usage indicate a localized cell tower outage.
Makes sense. A drop in traffic means the tower is down.
Right. They need to detect these drops with the least possible latency to automatically dispatch repair crews.
This scenario is fascinating because it actively tests your ability to unlearn relational database habits.
Yeah, how do people normally try to solve this?
Well, when presented with this, engineers instinctively look for database-native solutions. They'll suggest configuring an Aurora database activity stream to monitor the data.
Which sounds like streaming.
It does. Or, worse, they'll write a Lambda function on a cron job that wakes up every 60 seconds, connects to Aurora, runs a select count star query, and compares it to the previous minute.
Oh, I hate that pattern. It's the are we there yet architecture. Pulling a massive relational database every minute just to count rows sounds like a great way to absolutely crush your database CPU and drive up your I/O costs.
It is incredibly inefficient. But let's deconstruct the core failure here. By the time your telemetry data is resting comfortably on disk inside a relational database like Aurora, you've already lost the battle against latency.
The data is already old.
Think about the life cycle. The data was generated, it traveled the network, it hit a load balancer, it hit an app server, the app server opened a database connection, it initiated a transaction,
Aurora wrote it to a write-ahead log.
and then finally committed it to storage. By the time you query it, the cell tower outage has already happened. Customers are already angry and switching carriers, and your system is just now doing the math to realize something is wrong.
That's a great point. And what about the database activity stream idea? Because that really does sound like it would work.
It's a fundamental misunderstanding of the feature itself. Database activity streams are a security and auditing feature.
Oh, like for compliance.
Yes. They stream metadata about database events to Kinesis. Things like who ran an alter table command, or if a user failed a login attempt 10 times.
Right, who is doing what?
Exactly. They're absolutely not designed to inspect the actual business payload, in this case, the cell tower telemetry that's being inserted.
So we have to intercept the data earlier.
Yes. The definitive pattern here is shifting the analytics to the left.
Shifting to the left, I like that.
You modify the ingestion application to publish the raw telemetry directly to Kinesis data streams first. Then you deploy Apache Flink to calculate the moving averages and detect the drop in volume while the data is still in transit.
I want to make sure I really understand this, though. Flink isn't just a router, right? How does it actually know there's a drop without looking back at historical data in a database?
That is the magic of stream processing. Flink maintains internal state.
Okay.
You can configure a sliding window of, say, 10 seconds. As millions of records fly through, Flink keeps a continuous rolling tally in its own memory.
It's doing the math on the fly.
Exactly. If the volume in the current 10-second window drops 50% below the volume of the previous window, Flink instantly triggers an alert to an SNS topic.
So it detects the anomaly before the data even finishes its journey to the database.
Think of it like this. If you need to know a building is on fire, you don't wait for the fire department to file a written report in a filing cabinet and then have an intern check the cabinet every hour.
Right.
You install a smoke detector in the hallway. Flink is the smoke detector. Aurora is the filing cabinet.
The smoke detector versus the filing cabinet. That perfectly encapsulates the shift to event-driven architecture.
That's a huge mindset change.
It really is. But okay, let's turn the page. Because whether you are running stream processing with Flink or massive batch jobs, you are consuming compute resources.
Oh yes, the bill always comes due.
Always. And this brings us to one of the most persistent, expensive problems in cloud engineering. Engineers drag their legacy, on-premises server-sizing mentalities into serverless environments.
It causes profound inefficiencies.
Let's unpack the secret life of serverless resources. Let's look at a seemingly simple problem. We have an AWS Lambda function. Its job is to read semi-structured data from S3, clean it up using some heavy regular expressions, and output clean JSON.
Okay, computationally heavy.
Very. The developers notice performance is abysmal. The function is timing out constantly. They look at CloudWatch metrics and see the Lambda function is pegged at 100% CPU utilization.
Not good.
No. And the function is currently configured with 128 megabytes of memory and a 15-second timeout limit.
When presented with this dashboard, a timeout error, and a maxed-out CPU, the instinctive reaction is to treat the symptoms rather than the disease.
Right, they just want to make the error go away.
Exactly. Engineers will look at the configuration and say, well, it's timing out after 15 seconds. Let's just increase the timeout to 30 seconds.
Which is so funny to me.
Or they'll suggest wrapping the invocation in a step function with automatic retries.
But wait, if my application is stuck at 100% CPU because my regular expressions are computationally heavy, giving it 30 seconds instead of 15 seconds doesn't make it process faster.
No, it doesn't.
It just lets it struggle and gasp for air for twice as long before it eventually succeeds or dies again.
Yeah.
And retrying a failing compute-bound job is just paying for the failure multiple times.
It's a total Band-Aid. But the deeper misunderstanding here is how AWS actually provisions serverless compute.
How does it work under the hood?
Well, in a traditional data center, or even when launching standard EC2 instances, you can mix and match. You can say, give me 2 CPU cores, but I only need a tiny amount of RAM.
Right.
Or give me a massive 64 gigabytes of RAM, but only 1 CPU core. You have independent dials.
Right. If my laptop's processor is maxed out rendering a video, buying more RAM and sticking it in the motherboard doesn't magically speed up the processor. That's the mental model everyone brings to the table.
And that is the exact mental model you must abandon when working with AWS Lambda.
Oh, really?
Yes. In Lambda, there are no independent dials. CPU allocation is strictly mathematically proportional to memory allocation.
Wait.
You cannot go into the AWS console and say, I want a faster processor for this Lambda function. The only dial available to you is memory.
So if I buy memory, I'm secretly buying CPU.
Yes. In the context of Lambda, buying memory is buying a proportionately larger slice of the underlying physical hardware.
That is wild.
When you increase the memory allocation from 128 megabytes to 512 megabytes or 124 megabytes, AWS automatically, implicitly provisions proportionally more CPU compute power, more network bandwidth, and more disk I/O to your function.
So the systems engineering solution to a CPU-bound Lambda function isn't extending the timeout, it is increasing the memory.
Correct.
But wait, let me play devil's advocate here. As a cloud architect, I have a budget. If my function is only utilizing 40 megabytes of memory to hold the S3 object, provisioning 512 megabytes sounds like a massive, irresponsible waste of money just to get the CPU upgrade.
It sounds totally counterintuitive until you look at the billing model.
Okay, break the math down for me.
With Lambda, you are billed based on the amount of memory provisioned multiplied by the exact execution time in milliseconds.
Right.
If you run it at 128 megabytes, you have a very cheap hourly rate, but your computationally heavy function might take 12,000 milliseconds to finish because it's completely starved for CPU.
Okay.
If you bump it to 512 megabytes, your rate per millisecond goes up. However, because you now have 4 times the CPU power, the execution time might drop to, say, 1,500 milliseconds.
Oh, wow.
You're paying a higher rate, but for a significantly shorter duration. In many CPU-bound scenarios, over-provisioning memory actually reduces your total AWS bill because the function finishes so much faster.
You spend more per millisecond, but you run for so drastically fewer milliseconds that you win the math equation.
Exactly. It's a massive paradigm shift.
Now, contrast that invisible serverless allocation with a scenario where you do have explicit control over the hardware infrastructure. Let's talk about Amazon EMR, Elastic MapReduce.
Okay, big data time.
A team is running a massive daily Apache Spark job to crunch petabytes of clickstream data. They deployed a cluster using general-purpose EC2 instance types, like the M5 family, for their core and task nodes.
Pretty standard starting point.
Right. The cluster scales up automatically, but when they look at the ganglia metrics, they notice something alarming. The CPU utilization across the task nodes is completely maxed out, but the memory utilization never goes above 30%.
And they want to optimize the cluster to reduce their monthly spend.
Exactly. What do?
This requires the exact same diagnostic skill as the Lambda scenario, identifying the true resource bottleneck, but the solution is the exact inverse.
Because they have control.
Here, they have explicit control over the hardware profile. The M5 general-purpose instances provide a balanced ratio of CPU to memory, which is great for web servers.
But not this Spark job.
Right. This specific Spark job is clearly compute-bound. It requires intense processing power to calculate aggregations, but it isn't holding massive data frames in memory.
They are basically renting a fleet of giant expensive moving trucks just to deliver a bunch of small, heavy lead weights.
That is a perfect analogy.
They are paying for massive empty cargo space, the memory that they just aren't using.
Spot on. So the architectural move here is to switch the task nodes from the general purpose and family to compute-optimized instances, like the C5 or C6G family.
Because those have a different ratio.
Compute-optimized instances give you a significantly higher ratio of virtual CPUs to memory. More importantly, they cost less per CPU core than the general purpose equivalents.
So you align the hardware with the workload constraint?
By aligning the physical instance family to the specific constraint, you get the processing power you need while shedding the cost of the unused RAM.
It all comes down to identifying the bottleneck. CPU versus memory versus network. If you don't know what resource your workload is starving for, you are just blindly throwing money at Jeff Bezos.
Basically, yeah.
Okay, so we've optimized our compute. The Lambda functions are breathing easily. The EMR clusters are perfectly sized. But in a modern data platform, no single compute job exists in isolation.
They all have to talk to each other.
You have to string these tasks together into a cohesive, reliable pipeline. Which brings us to a major architectural plague. Orchestration ceilings and the duct tape architecture.
Oh, the duct tape. The cloud is full of incredibly powerful primitive tools. But when developers find a tool they love, they tend to abuse it.
And Lambda is the golden child.
AWS Lambda is the ultimate victim of its own success. It is so easy to deploy that it becomes the golden hammer, and suddenly every orchestration problem looks like a nail.
Let's look at a classic orchestration breakdown. A data engineer is tasked with building a nightly reporting pipeline. They need to execute a series of complex SQL queries using Amazon Athena against a massive data lake.
Okay.
The business requirement is that these queries must run sequentially, and here is the fatal constraint. Based on historical data, each Athena query can take up to 20 minutes to complete.
20 minutes. And if you consult the hive mind on how to automate this, a terrifying number of people will suggest writing a Python script, packaging it into an AWS Lambda function, and using Amazon EventBridge to trigger it every night.
Right, just a simple cron job.
The Lambda function would use the Boda 3 SDK to submit the query to Athena and then write a while loop that just checks the status every 10 seconds until it finishes.
It makes sense on a whiteboard. I need code to run, I'll use Lambda. But we just talked about the constraints of Lambda.
It makes sense until you hit the hard, non-negotiable ceiling. AWS Lambda has a maximum execution timeout of exactly 15 minutes.
You can't extend it.
It cannot be extended. You cannot call support and ask for an exception. If your Athena query takes 15 minutes and 1 second to execute, the Lambda function that is waiting for the result is unceremoniously terminated by the AWS infrastructure.
Just dead.
Just dead. And this creates a devastating silent failure scenario.
Why?
Because the query itself might actually finish successfully over in the Athena service 5 minutes later.
Yeah.
But the Lambda function, the orchestrator that was supposed to trigger the next step in the pipeline, is gone.
Oh, wow.
Your pipeline breaks in half, no further steps are executed, and it's incredibly difficult to debug because there is no error in the SQL logic.
The failure is entirely in the orchestration layer's inability to wait.
This is duct tape architecture. It works with small data sets, but the moment you put it under the tension of a large workload, it snaps.
So if Lambda is structurally incapable of waiting for long-running asynchronous jobs, what is the correct architectural pattern? How do we orchestrate a 20-minute query without building a fragile custom application?
The only robust pattern here is AWS step functions.
Step functions.
Step functions are state machines built explicitly for orchestration. You define a workflow using JSON. The first state uses the native integration to call the Athena Start Query Execution API. Then, crucially, you transition into a wait state.
But wait, aren't step functions expensive? I've heard horror stories of people racking up massive bills because they use step functions instead of Lambda.
That is a brilliant point, and it's why understanding the pricing model is part of architecture.
How does it bill?
Standard step function workflows are billed per state transition, not by the duration of the wait time.
Oh.
If you use a Lambda function to wait for 15 minutes, you pay for 15 minutes of compute time, while the function literally does nothing but sleep.
Paying for it to do nothing.
Right. If you use a step function, it triggers the query. That's one state transition. It enters a wait loop. That's another transition. You can wait for an hour, a day, or up to a full year.
And you don't pay for that.
You pay absolutely nothing for the idle time while it waits. It periodically wakes up, checks the get query execution status, and when it's successful, moves to the next step.
It separates the action of executing from the burden of waiting.
You get guaranteed execution, infinite patience, and zero idle compute costs.
That is profound. You are moving from imperative programming writing while loops and sleep statements in Python to declarative orchestration.
Exactly. Tell the cloud what you want, not how to do it.
Let's look at another scenario that demands this declarative approach. We have an engineering team loading massive flat files into an Amazon Redshift data warehouse every night.
Okay, heavy lifting.
Once a table is completely loaded, they need to update a central tracking dashboard, which is powered by an Amazon DynamoDB table. They've already written a Lambda function that handles the DynamoDB update.
So they just need to trigger it.
Right. The question is, how should they trigger that Lambda function the exact moment the Redshift load finishes?
The legacy reflex, the anti-pattern, is to create a chain of dependencies. Someone will suggest modifying the script that loads Redshift to also directly invoke the Lambda function.
Tying them together.
Or they'll suggest running a second Lambda function on a schedule that constantly queries Redshift to ask, are you done yet?
The polling anti-pattern again?
Exactly. Tight coupling. If the Lambda function experiences a transient error or a permissions issue, the Redshift loading script might crash trying to invoke it.
Bringing down your data warehouse ingestion just because your metadata tracker failed.
Terrible architecture.
So how do we decouple them? How do we build a robust nervous system where the right hand knows what the left hand is doing, but they aren't physically tied together?
You leverage the true nervous system of the AWS cloud, which is Amazon EventBridge.
Yes, I love EventBridge.
The architectural solution is to configure the Amazon Redshift Data API to publish a state change event directly to EventBridge. Then you configure an EventBridge rule to listen for that specific event and route it to your Lambda function.
I love explaining EventBridge to people. Think of EventBridge as a massive central post office for your entire cloud infrastructure.
It's a great way to look at it.
Redshift doesn't know about DynamoDB. It doesn't care about Lambda. When it finishes loading a table, it just yells out a highly structured JSON message into the void of this post office. Hey, I just finished loading the sales data table at 2:00 a.m.
That is the essence of event-driven architecture. Redshift acts purely as an emitter. It offloads the event and goes back to its primary job of being a database.
And EventBridge handles the routing.
In EventBridge, you define a rule with an event pattern. The event pattern is essentially a JSON filter. It constantly scans the stream of millions of events flowing through the post office, looking for a payload where the source is oz.redshift, and the detail type is statement execution status change with a status of finished.
And when it sees a match, it grabs the envelope and hands it to the Lambda function.
Exactly. This drastically reduces operational overhead. You write zero polling code. You configure zero retry logic in your source application.
And what if the Lambda is down?
If the Lambda function is temporarily down, EventBridge can automatically queue the message in a dead letter queue for later processing. Redshift is completely unaffected. You achieve perfect decoupling.
Okay, this is a perfect transition into our next major domain. We've routed the networks, we've handled stream latency, we've optimized our compute, and we've orchestrated the pipelines.
The data is flowing beautifully.
Flowing beautifully into our data lakes. But as that data grows, and as more and more departments want access to it, we hit the absolute biggest friction point in modern enterprise architecture: governance. Who is allowed to see what?
It is the paradox of big data.
How so?
The business spends millions of dollars building a centralized data lake to democratize data access, right? And the very next day, the chief information security officer locks the entire thing down because it's too risky.
Yeah, nobody gets access. Let's explore this through the lens of a data mesh topology. This is a critical concept. We have a massive global retail organization. They've transitioned from siloed databases to a central S3 data hub. Analysts from 50 different countries need to query this hub to build their localized sales forecasts. But strict data sovereignty laws dictate that a data analyst in Germany can only see rows of data pertaining to German customers. An analyst in Japan can only see Japanese customer data. This is classic row-level security.
And if you look at how developers historically tried to solve this, and how they still suggest solving it in forums today, it is a study in operational masochism.
What do they do?
The immediate instinct is to say, okay, we will write a nightly ETL job that reads the massive central table, filters out all the German records, and writes them to a brand new table or S3 bucket called Sales Germany.
Oh, no.
Then we do it again for Sales Japan. Then we create 50 different IAM roles and grant the German analysts access to the German bucket.
Just saying that out loud sounds exhausting. Think about the physical realities of that architecture. If you have 50 countries, you're now paying to store 50 duplicate copies of your data.
The storage costs alone.
You have to maintain 50 different ETL pipelines. If a column name changes from customerid to cliented, you have to go manually update 50 different SQL scripts. It is a fragile, brittle nightmare.
It is the absolute antithesis of least operational effort. You are attempting to solve a governance problem with a data engineering brute force approach.
So what's the AWS way?
AWS recognized this was a massive pain point. You need a centralized mechanism that intercepts the query and dynamically filters the data based on the identity of the person asking without duplicating the underlying storage.
Enter AWS Lake Formation.
Exactly. AWS Lake Formation is the definitive solution for granular data governance on S3 data lakes.
How does it replace the IAM bucket policies?
Instead of giving users direct IAM permissions to the S3 bucket, which is essentially an all-or-nothing proposition, you register the S3 bucket's path with Lake Formation. From that moment on, Lake Formation brokers all access.
How does that actually work mechanically? Does it copy the data secretly?
No, the data stays exactly where it is in S3. One copy. You go into the Lake Formation console and define data filters.
Okay.
You create a rule that says if the principal making the request belongs to the Germany analyst group, apply this SQL-like filter, where country code equals DE.
So it's dynamic.
Yes. When the analyst opens Amazon Athena and runs select star from global sales, Athena passes their identity to Lake Formation. Lake Formation evaluates the data filter, dynamically injects the where clause, reaches into S3 using temporary scope-down STS credentials, and returns only the authorized rows back to Athena.
It happens completely invisibly to the user. One single copy of the data in S3. 0 ETL jobs to maintain. Massive reduction in operational overhead.
It's beautiful.
But row-level security is only half the battle. What happens when the security requirement is inside the data itself? Let's look at the dynamic PII redaction.
Oh, personally identifiable information. The really sensitive stuff.
Right. We have a multi-terabyte e-commerce data set sitting in S3. It contains PII, like social security numbers, credit card numbers, and email addresses. The data science team needs to use this data set to train machine learning models, so they absolutely cannot be allowed to see the PII.
Standard compliance.
But the customer service application needs to read that exact same data set and must see the PII to verify caller identities.
This is where traditional architectures truly break down. The legacy approach is exactly what we just discussed. You run an ETL pipeline to strip the PII out and create a sanitized duplicate copy for the data scientists.
And you are paying for double the storage again.
And taking on the burden of keeping the data set synchronized. If a customer exercises their right to be forgotten under GDPR and asks you to delete their data, you now have to hunt down their records in the raw bucket, the sanitized bucket, the dev bucket.
It's a compliance landmine, so we need a way to sanitize the data on the fly, just like Lake Formation did for the rows. But S3 is just a dumb object store.
It just hands you the file.
Right. When you call an S3 get object API, it just blindly returns the file. How do we inject intelligence into a raw file download?
You use one of the most brilliant architectural features AWS has released in recent years, which is S3 Object Lambda.
I have to admit, the first time I saw S3 Object Lambda in action, I thought it was literal magic.
It's an incredible piece of engineering. S3 Object Lambda allows you to fundamentally alter the behavior of the S3 Get Object API by injecting custom compute a Lambda function directly into the read path.
How does that work mechanically?
Here's how it works. You don't give the data scientists the direct ARN of the S3 bucket. Instead, you create an S3 Object Lambda access point.
Okay, a different front door.
Exactly. When a data scientist queries the data through this access point, their standard HTTP GEG request is intercepted by AWS infrastructure.
Before it ever touches the physical hard drive where the data lives.
Yes. The access point triggers a Lambda function that you have written. That Lambda function receives the context of the request, who is asking, and what object they want.
So it knows it's a data scientist asking.
Right. The Lambda function itself executes a standard getObject call to the underlying bucket, retrieves the raw data containing the PII into its own execution environment memory, runs your redaction logic to mask the social security numbers with asterisks, and then streams the modified data back to the data scientist.
Wait, I have to play devil's advocate again here.
Go for it.
If we are injecting a Lambda execution, spinning up a micro VM, downloading the file, running a regex, and streaming it back into every single S3 read request, Doesn't that add massive latency? Won't the analytics team scream about performance degradation?
That is a phenomenal systems engineering question, and it highlights the core trade-off of architecture. Yes, you are absolutely introducing latency.
You have to.
You are paying a penalty of perhaps a few hundred milliseconds or even seconds, depending on file size, for the compute time. But as an architect, you have to weigh that performance penalty against the alternative.
The duplicate buckets.
The alternative is storing duplicate data, maintaining fragile ETL synchronization pipelines, and carrying the massive compliance risk of PII proliferation. You are trading a small amount of read latency for an astronomical reduction in operational overhead and security risk.
You are transforming the data as it is being read completely dynamically without ever storing a second copy. This is the defining characteristic of modern governance on AWS.
Least operational effort.
Exactly. It points you aggressively toward managed interception services, lake formation for row and column filtering, S3 object lambda for inline data transformation. You prioritize these capabilities over building custom pipelines that physically move and duplicate data.
You govern access, not copies.
Okay, we're rounding the final corner. Let's talk about the physical reality of the disks spinning in an AWS data center.
The bare metal.
We've secured the data. We are governing it flawlessly with lake formation. But how we physically store the bits and bytes dictates the baseline performance of every query we run and directly drives our monthly AWS bill. Welcome to storage economics and the small files problem.
Storage is the bedrock. If you get the physical layout wrong at the storage layer, no amount of Lambda memory allocation or EMR instance optimization will save you.
You can't compute your way out of it.
You cannot outcompute a fundamentally flawed storage design.
Let's talk about the absolute bane of a data engineer's existence, the small files problem.
Oh, it hurts just hearing it.
We have a company building an S3 data lake. They have IoT devices pushing thousands of tiny 50 kilobyte to 100 kilobyte Parquet files into S3 every single hour.
Just a constant drizzle of tiny files.
Right. They are evaluating open table formats like Apache Iceberg to manage this. The critical requirement is that they need to optimize query performance so their Athena queries don't slow to a crawl over time as these millions of tiny files pile up.
To understand why this is such a catastrophic anti-pattern, we have to look at the mechanics of distributed big data engines like Amazon Athena or Redshift Spectrum.
How do they like to read data?
These engines are designed to scan massive data sets by reading large, contiguous blocks of data sequentially from disk. They love big 256 megabyte or 512 megabyte files.
Big chunks.
When an engine has to read a file, it first has to execute an S3 API, call a metadata operation, to open the network connection, find the file, read the header, and locate the data blocks.
So it takes time just to shake hands with S3.
Precisely. Now imagine a 50 kilobyte file. The engine spends perhaps 100 milliseconds negotiating the network connection and reading the metadata, and only 2 milliseconds actually reading the payload data.
Wow, that ratio is terrible.
So multiply that by 10 million files.
Mm-hmm.
The engine spends 98% of its total execution time just opening and closing network connections. The query performance falls off a cliff.
And it costs money too, right?
Furthermore, S3 charges you for every single GET request. Reading 10 million tiny files will bankrupt you in API call fees alone.
So the data is fundamentally fragmented. The HiveMind forum solution to this is almost universally option A. Write a custom AWS glue job using PySpark. Schedule it to run at 2:00 a.m. every night.
The classic compaction job.
Yeah. Have it read all the thousands of 50 kilobyte files for that day's partition, merge them together in memory, and write out a single 500 megabyte file. Then update the data catalog.
And yes, mechanically, that solves the read performance issue. But look at the operational overhead.
That's a lot of code.
You have just committed your team to writing custom PySpark code. You have to manage the orchestration of that job. What if the job fails halfway through? You have partial data.
What if someone queries during the job?
Exactly. What if a data scientist tries to query the data while the compaction job is running? They might get duplicate records or missing records. You are taking on an immense amount of state management.
So how do we escape the compaction maintenance loop? How do we fix the physical layout without writing code?
You leverage the architecture of modern open table formats. The correct approach is to use Apache Iceberg integrated with the AWS Glue data catalog, and specifically configure Iceberg's table properties for automatic compaction.
How does Iceberg do it differently? Doesn't it still have to rewrite the files?
It does rewrite the files, but the paradigm shift is where the responsibility lies. In the legacy Hive Metastore model, the catalog just points to a folder in S3, and it's up to you to manage the files inside it.
Right.
Apache Iceberg fundamentally changes this by maintaining its own intricate metadata, tree manifest lists, and manifest files that track every single data file at the object level.
It tracks everything.
Because Iceberg completely controls the transaction log, it can perform automatic compaction in the background safely.
Safely, meaning without corrupting active queries.
Exactly. Iceberg provides snapshot isolation. You configure table properties that say when the average file size drops below 10 megabytes, trigger compaction.
And it just handles it.
Iceberg will automatically spin up the necessary compute, often managed by Athena or Glue in the background.
Sure.
Read the small files, write the new large files, and then atomically swap the pointer in its metadata tree.
So the user never sees the mess.
To a user querying the table during this process, they just see the old snapshot. The moment the compaction finishes, the next query seamlessly reads the new optimized large files. You are configuring the system's behavior through properties, not coding fragile operational jobs.
You are telling the system what state you want it to maintain, rather than programming how to do it. That is the essence of modern data engineering.
100%.
Okay, final scenario. Let's look at the pure economics of storage tiers. We have an enterprise with petabytes of historical data spread across thousands of S3 buckets.
A lot of data.
The access patterns are completely unpredictable. Some datasets are queried heavily for a week and then not touched for 6 months. Other datasets are accessed randomly throughout the year.
Hard to plan for.
But, and here is the absolute hard constraint that dictates the entire architecture, when a user does execute a query, that data must be retrieved and returned in milliseconds. The CFO has demanded they optimize the S3 storage costs.
The cognitive trap here is relying on the traditional tools that engineers have used for the last decade, which are standard S3 lifecycle policies.
Right, moving data around based on age.
It is incredibly tempting to look at a cost optimization prompt and say, I know this. We will create a lifecycle rule that transitions objects to S3 standard infrequent access after 30 days, and then transitions them down to S3 Glacier flexible retrieval after 90 days.
Why is that an architectural dead end? Moving old data to cheaper storage sounds like exactly what the CFO wants.
Because it completely ignores the two critical constraints: unpredictable access and millisecond retrieval. Let's look at standard IA first.
Data infrequent access.
Right. Standard IA offers a lower monthly storage cost per gigabyte, but it introduces a data retrieval fee per gigabyte read.
Oh, right.
If your access patterns are truly unpredictable, a data set might age out to 30 days, transition to IA, and then suddenly become the subject of a massive analytical query. You will get hit with astronomical retrieval fees that completely erase any storage savings you achieved.
You save pennies on storage to pay dollars in retrieval.
Exactly. But the second constraint is even more restrictive. The prompt explicitly requires millisecond retrieval latency.
And Glacier isn't fast.
S3 Glacier Flexible Retrieval and S3 Glacier Deep Archive are asynchronous offline storage classes. The data is fundamentally parked on different physical media.
Like actual tape drives in some cases.
Exactly. When you request a file from Glacier, it takes minutes or sometimes up to 12 hours to quote-unquote thaw the data and make it available. If you use a lifecycle policy to push data to Glacier and an analyst queries it with Athena, the query will simply fail because the data cannot be accessed in milliseconds. You have violated the core business requirement.
So we are stuck. We can't use Glacier because of the latency, and we can't use standard IA because the unpredictable access will bankrupt us with retrieval fees. Do we just leave it all in the expensive S3 standard tier?
No. AWS built a specific storage class to solve this exact mathematical paradox: S3 intelligent tiering.
Break down the mechanics of intelligent tiering. How does it actually work under the hood to satisfy both constraints?
Intelligent tiering is brilliant because it leverages metadata tracking at a massive scale. When you move an object to the intelligent tiering storage class, AWS internally tracks the last access time of every single object.
Okay.
By default, it operates with two primary access tiers: a frequent access tier, which is priced identically to S3 standard, and an infrequent access tier, which is priced identically to standard IA.
Okay, so far it sounds just like a lifecycle rule.
But here is the critical divergence. If an object hasn't been accessed for 30 consecutive days, the intelligent tiering mechanism automatically moves it to the infrequent access tier to save you money.
Okay.
However, if an analyst suddenly runs a query that touches that object on day 45, the system automatically moves it back to the frequent access tier. And here is the magic. It does this with absolutely no data retrieval fees, and it maintains millisecond latency performance no matter which tier the data is currently sitting in.
Wait, if there are no retrieval fees, How does AWS make money on this? Why wouldn't everyone just put 100% of their data in intelligent tiering?
Because there's a tiny fractional automation and monitoring fee charged per 1,000 objects every month.
Ah,
Intelligent tiering is a managed service acting on your behalf. For data sets with millions of tiny files, that automation fee can actually exceed the storage savings.
So we are back to the small files problem.
It all connects.
If you have optimized your data lake with Iceberg and you have large consolidated 500 megabyte files, that per object monitoring fee is practically zero and the storage savings are massive.
Exactly. The systems interconnect. By fixing the physical layout with Iceberg compaction, you unlock the ability to safely use intelligent tiering, guaranteeing you the absolute lowest storage cost for unpredictable workloads while completely preserving millisecond query performance. You just turn it on, and AWS's algorithms optimize the economics for you.
What a journey. If we step back and look at the whole picture, modern data engineering on the cloud is undergoing a massive evolutionary shift.
It really is.
We are fundamentally moving away from managing data movement. The era of writing thousands of lines of custom Python code to pull databases, extract data, run fragile compaction jobs, and manually manage storage tiers. It's ending.
It is becoming legacy architecture.
We are moving toward a paradigm of managing data, metadata, and configuring managed services. We navigated the hidden VPC routing rules of serverless components, proving that ENIs need root tables. We definitively distinguished the millisecond latency of stream processing with Flink from the micro-batching reality of Firehose.
We covered a lot of ground.
We fixed fragile orchestration timeouts by decoupling our systems with the declarative power of step functions and event bridge. We established a secure centralized data mesh using lake formation without duplicating a single byte of physical storage. And finally, we optimized our disk layouts with Iceberg to unlock the automated financial wizardry of intelligent tiering.
You are no longer just a writer of scripts. You're becoming an architect of massive, interconnected, distributed systems.
And as we wrap up this deep dive, it brings us to a final, provocative thought.
Lay it on me.
We've spent this entire hour ruthlessly optimizing our architectures for least operational overhead by leaning heavily into these sophisticated managed services. Event bridge, step functions, lake formation, MACI, object lambda. But what happens when the mandate for least operational overhead collides head-on with a mandate for maximum cost efficiency?
That is the ultimate tension. Managed services are not free. Nope. When you use lake formation or S3 object lambda, you are paying a premium for that convenience and security. At what point does the AWS compute bill for a fully managed governance service outweigh the engineering salary required to build and maintain a custom, albeit clunky, internal solution?
It's a tough call.
When you pass the DEA-C01 exam, you've proven you know how the tools work. But as you continue your career as a true cloud architect, balancing that terrifying equation time versus operational maintenance versus hard infrastructure costs, that is the real architecture you have to build.
That is the true muddy water we all have to swim in. I want to thank you, the listener, for putting on your hard hat and joining us in the trenches today. When you are staring at these scenarios on an exam, or, more importantly, when you are staring at a failing pipeline in production at 3 in the morning, I challenge you to look past the obvious, easy answers.
Don't just settle for knowing what the dashboard says.
Focus ruthlessly on the systems engineering why. Understand the microscopic mechanics of the services you are using. Because when the abstraction layer inevitably breaks, you're the one they're going to call to fix the actual machine underneath. Keep building, stay curious, and we will catch you on the next deep dive.